we will discuss about the important topics which is very useful in industry. That topics is thin pressure vessel, basically related to thin cylinder and sphere. So first we will just imagine a pressure vessel. It will be the better example if we take an egg, that is a good pressure vessel example. So take an egg, that surface can revolve with respect to some longitudinal axis by the speed omega. So now we'll try to understand what is pressure vessel is. Pressure vessel is a closed container having the form of surface of revolution subject to pressure by the fluids containing in it on its wall is called as pressure vessel. And that is here. This is the surface of the air which you can rotate about some axis. That is why surface of revolution subjected to pressure. You know, inside the air there are fluids, yellowish and whitish, that will cause the pressure on the surface of its wall of thickness T. So this is the pressure vessel. Now, if the wall thickness of such a vessel is small compared with its principal radii of curvature, that is R1 and R2 are the principal radii of the curvature, the wall will have very little bending resistance and acts primarily as membrane, in which stresses are tangential to the middle surface of the wall and acts uniformly distributed across the thickness of the wall. Now, we will just isolate an element which is broadly drawn in the detailed figure. And when we will isolate from this vessel, that element will be subjected to pressure force, that is P, ds1 and ds2 is the surface area over which the fluid pressure will exert, and try to take out this element towards outside. But for the equilibrium of the element, static equilibrium of the element, there will be resistance by the material of the wall of this pressure vessel. So that will be subjected to some stresses, sigma 1. Sigma 1 is the longitudinal stresses, sigma 2 is the circumference stresses. And the element dimension ds is small because of a small element dimension taken as a small quantity, that is ds1 and ds2. ds1 longitudinal dimension and ds2 is the circumference dimension. Now, this pressure force will be restricted by the longitudinal force and as well as circumference force. That is called stress resultant. So, stress, longitudinal stress sigma 1, corresponding material area ds2 into T. Circumference stress sigma 2, corresponding material area of the thickness is the ds1 T. These two stress resultant will restrict the pressure force. So now there will be a elemental analysis. If we taken one side, there is longitudinal dimensions like this, and it is subjected to stress resultant sigma 1 ds2 t, and here sigma 1 ds2 t, and pressure force will act outside. So here radius of curvature from this point, this is the O1 and R1. Now this elemental thickness, that is ds2 d theta 1 here. So we will resolve this component in vertical and corresponding component. Here we will first check out the angle. This will be say here theta 1 by 2 or half of this, and ultimately this angle will be d theta 1 by 2. So corresponding components, as this will be the here also this will be the d theta 1 by 2. So component of this cos and this will be sin. So this sin component will be sigma 1 ds2t sin d theta 1 by 2, and this will also have the same value and the cos component of this side and this side will balance each other. Similarly, if we take the circumferential side of this element, that will also result same phenomena. This will be your element of the circumferential direction that will develop the result here. This will be R2, this will be d theta 2. Here this result will be sigma 1 d sigma 1 ds2t. Here this result will be sigma 1 d ds2t. So here for the first component, this angle will become d theta 2 by t2, and this will also become d theta 2 by 2. This is the cos component. Here sin component will be sigma 2 ds2t. This one will be sigma 2, no, sigma 2. ds1, this will be ds1, and d theta 2. This component will be into sin d theta 2 by 2. Here will be sin component sigma 2 ds1 into sin of d theta 2 by 2. So, if we consider the static equilibrium of this element, then resultant force will be like this. Now we are erasing here clarity. So ultimate result of the equilibrium becomes like this: 2 sigma 1 ds2t sin d theta 1 by 2 plus 2 sigma 2 ds1t sin of d theta 2 by 2 is equal to pressure force that will be restricted P ds1 ds2. So R1 for the radius of curvature along the longitudinal axis, along the circumference respectively. Now from the principle of geometry we know ds1 is equal to r1 d theta for small case, and ds2 is equal to r2 d theta 2. Now for the small case we can write sin theta is equal to theta. So 2 sigma 1 ds2t sin, in place of sin d theta 1 by 2 we write d theta 1 by 2 plus 2 sigma 2 ds1t into d theta 2 by 2 is equal to p ds1 ds2. Now 2 cancel out. these two cancel out, these two cancel out. So result will be sigma 1 d s2 t d theta 1 plus sigma 2 d s1 t into d theta 2 is equal to d ds1 ds2. Now from this relationship we can get d theta 1 is equal to ds1 by r1, and from this we will get d theta 2 is equal to ds2 by r2. So we will replace it. So write down here sigma 1 ds2 t into ds1 by r1 plus sigma 2 ds1 t equal to ds2 by r2, that is equal to ds1 ds2. Now if we look into this balancing equation, the starting equation, that both the sides RH and LH having ds1 and ds2, ds1 and ds2 cancel out. We will cancel out. So equation becomes sigma 1 t by r1 plus sigma 2 t by r2 is equal to p. Cancelling ds1 ds2 terms. Now finally this equation will become, if you take out the common t, that will become, therefore we write sigma 1 by r1 plus sigma 2 by r2, that is equal to p by t. This is some important relationship will be developed from this condition. That is sigma 1 is the original state of the element or pressure state, and sigma 2 is the circumference stress. Sometimes it is called as group stress. So that will be circumference stress, the group stress. Group stress means that will basically hold the pressure thrust of the cylinder or sphere. This important relationship, that is sigma 1 by r1, that r this important relationship r how many markers? This importance relationship developed by of an engineer from ASA, American Society of Mechanical Engineers. Very important. Now, this general formula we will apply for cylinder first, then we will apply for sphere. Then how we will develop these spaces? Let us check. Now, so best we will take an example of cylinder and we will apply this theory. So, as an example, take some cylinder here. Cylinder, this is the element, cylindrical element. In this direction, we will write down our stresses sigma 2, and longitudinal direction will be written as sigma 1 and sigma 1. So, take the thickness of the cylinder as t, table thickness, and radius of the cylinder. If you look here, radius of the cylinder is r t. Now from this cylinder, from this we will find out the formula that is applicable for cylindrical analysis. So now if you consider here, then from this we will tell that r1 They will not meet. They will not meet at any point. And R2 will be radius of the cylinder. Now sigma 1 by R1 plus sigma 2 by R2 is equal to P by T. Pressure. Here pressure say P, acting is the cylinder. P. So from this we will write R1 is equal to substitute R1 is equal to infinity, and we will substitute R2 is equal to capital R. So that would become infinity plus sigma 2 by R is equal to P by T. So sigma 1 by infinity means this will be 0. So therefore we can say sigma 2 is equal to P R by T, represented in terms of radius. If you represent in terms of diameter, then it will be PD by 2T. So this is the usual formula for the cylinder of group stress, PD by 2T. Now we will also find out the value of sigma 1. Then basically now we will find out the sigma. Now condition is closed container means this is the cylinder and this is the stresses. So free pressure will act in this direction and the stresses will act in this direction. So sigma 1 cut position sigma 1. So from this we will get the value of sigma 1 into corresponding material area. Corresponding material area means this is the periphery times the thickness. So 2 pi r into P is equal to pressure force exerted on the ring here. That is equal to P into pi r square. So from this we will get the value sigma 1 is equal to P r by 2T. That will become in diameter terms P D by 4T. So these are the usual formula for the cylinder. So ultimately, what will be the result of cylinder? That is, if we look into this, sigma 2 is equal to PD by 2T and sigma 1 is equal to PD by 4T. That is, we can say here, oops, the sigma 2 is equal to 2 times of sigma 1. So in this case of cylinder, the sigma 2 will be the governing stress. When sigma 2, when a cylinder subjected to pressure, then sigma 2 will be as much as greater than of sigma 1. So sigma 2 will be the governing stress. Now we will take the example of sphere for finding out of that stresses. Suppose it is a sphere and we will take an element over its equator. So this side is sigma 1, this side is sigma 1, this side is sigma 2, this side is sigma 2. Thickness of the cylinder plus sphere P and corresponding radius say R, capital R. So in this case R1 is equal to R2, that is equal to R. And therefore, if R1 is equal to, so therefore sigma is equal to sigma 2. So we will apply here formula sigma 1 by R1 plus sigma 2 by R2 is equal to P by T. So that will become 2 sigma here, in case of sphere, we are getting that circumference shape as well as hoop stress, circumference that is, and longitudinal stress are equal. So both the stresses will be governing in this case, and that value is PD by 40, which is less than your cylindrical governing stress. So basically, from the ease of manufacturing, cylinder can be easily manufactured. This is why usually for low pressure and moderate pressure, cylindrical vessels are used. For the large capacity and high pressure, we will apply the spherical vessel or spherical